Hey everyone, today we're excited to present to you our Capstone project. Astrophotographers want to take beautiful pictures of the night sky, just like the one we see right over here. Lately, though, their long exposure images have been coming out looking more like this. Indeed, not very beautiful, right? With the exponentially increasing number of satellites going into orbit every single year, especially with ventures like Starlink and Amazon's Project Kuiper, the light pollution from these reflections of these satellites is leaving satellite streaks and images, effectively ruining these photos. This is actually an issue that has been picking up a lot of traction in the astrophotography community, and here are just some very recent news article headlines addressing this issue. Current solutions do exist, but they all involve post-processing these images after the satellite trails have been left on them. For example, a popular solution is to actually stack multiple images together, which effectively removes the satellite streaks by averaging out the noise. However, this requires users to take multiple shots of the night sky, which is very time-consuming and very expensive. But what if there was a way of knowing exactly when the sky is clear before you even take any shot? Introducing Satellitecatcher.ca.
So say an astrophotographer wants to take a picture of the sky with no satellite interference. By just specifying a few telescope parameters and the telescope's pointing direction to our program, we perform calculations to find out exactly which satellites will interfere with the user's FOV and when. We then present this information in a way that's simple and efficient for the user to understand using a user interface and an API endpoint that anyone can access online through our website. This has potential of drastically reducing the work that astrophotographers need to put in to get beautiful looking pictures like the ones we saw earlier.
Awesome. Here's a little demo of exactly how our application works. So here's the landing page, and we can see it's running on Satellitecatcher.ca. Now here, users are actually able to enter their information like their relative position on Earth, their field of view size, and their exposure time, as well as exactly where the telescope is pointing to in the night sky. Once they've entered this information, they simply hit the search bar, at which point, basically, we scan the area around that sky, and we'll actually go through the algorithm that we use to do this. Now, we actually see the intersecting satellites in real time, exactly where the telescope is pointing. We can also hover over the satellites to see, to get more information, for example, their name and their NORAD IDs.
Now let's dive into the actual algorithm behind this project. Our state-of-the-art algorithm requires telescope location, orientation, and specifications to determine when the FOV is clear of satellites. To determine which satellites interfere with the telescope's camera, the algorithm progressively scopes down the number of satellites to consider in 2 steps. It first determines which satellites are in the correct altitude range from the point of view of the observer. It does this by considering all the satellites in an altitude band as seen in this image. Next, these satellites in the band are taken and we narrow based on a conservative approach by creating a safety range around the field of view. Here, we assume that satellites travel at their fastest possible speed directly to the center of the FOV. This effectively gives us the smallest set of satellites that are likely to interfere with our exposure. After we have this set, we call the N2YO API to get their exact positioning data in the length of the exposure. Lastly, we calculate the angular distance between the telescope's FOV and the satellite's position to determine which ones will actually interfere with our field of view and at which seconds in the exposure this interference will happen.
So that's what our project is currently doing, but a possible future application of it would also involve integrating it with telescope hardware directly so it can automatically capture photos when there's no satellite interfering. This is something that we already know will be worked on by future Capstone teams, and it will involve setting it up with Nina Suite, a popular way of interfacing between software and telescope hardware. Another application would be using our algorithm that we developed to build a tool that would allow large observatories to determine which areas of the sky are safe for viewing without interference on a particular night. This has potential of saving thousands of dollars, as these large systems are very costly to operate for a long time. For immediate next steps, we've also been fortunate enough to catch the eye of members of the astrophotography community already and have been invited to present our project at a popular podcast. We're also considering presenting this project at a Royal Astronomical Society of Canada conference. Thank you for listening.